magnetic field induction at a point on the axis of a current carrying long straight conductor. Magnetic field induction at a point on the axis of a current carrying long straight conductor. So in the diagram, XY is a long straight conductor through which a current I flows from X to Y, and P is a point at a perpendicular distance, I be the current which is flowing from X to Y, and P is a point at which we have to find the magnetic field induction. The point P is at a perpendicular distance A from the conductor XY. The oblique distance YP of the end Y from the point P makes an angle phi 2, and the oblique distance of the end X from the point P makes an angle phi 1 with the perpendicular distance. The magnetic field induction at the point P, magnetic field induction at the point P the magnetic field induction at the point P at a perpendicular distance A at a perpendicular distance small a, perpendicular distance A, from straight conductor XY, from the straight conductor XY carrying current I, magnetic field induction at the point P at a perpendicular distance A from a straight conductor XY carrying a current I is given by B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1 bracket closed. B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1, which is equation 1. So this is the expression of magnetic field induction at the point P due to a straight conductor XY carrying current I. That is B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1. Now that means at the point P we have to find the magnetic field induction, and the expression of magnetic field induction is acts according to the equation 1. And at P, magnetic field induction B acts inwards. Magnetic field B acts inwards at the point P. If the point P exists on the axis of the cylindrical straight conductor XY of infinite length, then so this is in the diagram, O be a point on the axis of the straight conductor, XY be the cylindrical straight conductor, and P is a point which exists on the axis of the cylindrical straight conductor XY of infinite length. . Now the distance of the point P from the point O is small r. Now vector OP is parallel to vector OY. That means OP is the distance of the point P from the point O. Vector OP is parallel to vector AY, and angle subtended by the distance of the end Y with respect to the point P is phi 2 is equal to 0 degree. And also that means we are considering a current element I vector dl or an elementary portion AC of the conductor, and the distance of the point P from the current element is R or vector OP, and that is parallel to the distance of the end Y OY. That's why phi 2 is equal to 0 degree. And also vector OP is anti-parallel to the index, anti-parallel to the distance of the index from the point O. That is, vector OP is anti-parallel to vector OX. Hence, the angle subtended by the index is 180 degree. Phi 1 again B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1. Sin phi 2 plus sin phi 1. Putting these values, the values of phi 2 and phi 1, we get mu 0 by 4 pi I by A sin 0 degree plus sin 180 degree. Therefore, B equal 0, because sin 0 degree is 0 and sin 180 degree is 0, is also 0. So finally we get the magnetic field induction at a point on the axis of a long straight conductor or a straight conductor is 0. Hence, the magnetic field induction at a point P, the magnetic field induction at a point P on the axis of a current carrying straight conductor on the axis of a long straight conductor or straight conductor. It may be straight conductor or long straight conductor is 0. If the point P exists on the axis of a straight conductor, then magnetic field B will be 0. Additional information: we can draw the graphical variation of magnetic field induction with the distance from the axis of the conductor. This is the cylindrical straight conductor. We are drawing a cylindrical straight conductor, and the axis of the cylindrical straight conductor is xy. This is xy is the axis of this cylindrical straight conductor. O be a point on the axis and P be a point on the surface of the cylindrical straight conductor. We can extend this distance. Now, magnetic field induction from the axis to the surface of the cylindrical straight conductor is directly proportional to distance. perpendicular distance, and outside magnetic field induction is inversely proportional to the distance. At the point 2, magnetic field induction is 0. Now if we draw the graphical variation of at, at the point O r equal to 0 and at the point P r is equal to capital R, means radius of the cylindrical straight conductor, radius of the cross section of the cylindrical straight conductor. And if we draw variation of magnetic field induction with the distance, magnetic field induction is plotted along y-axis and the distance is plotted along x-axis. Magnetic field induction increases with the distance from the axis to the surface of the cylindrical conductor, and beyond the surface of the cylindrical conductor, magnetic field induction decreases. From axis to the surface, magnetic field induction is directly proportional to the distance, and beyond the surface of the cylindrical conductor, it is inversely proportional to the distance.